Good evening, all the participants. Kindly update your display name into your ATAL ID. Once again, kindly update your display name into your ATAL ID. Dear participant, keep the microphone on mute. Use the chat box responsibly. So participants are requested to submit daily feedback after session. Minimum 80% of attendance is mandatory to receive the certificate. Dear participant, kindly update your display name into your ATAL ID. So dear participant, keep the microphone on mute. Use the chat box responsibly for questions and relevant discussions. Participants are requested to submit daily feedback after session. Minimum 80% of attendance is mandatory to receive the certificate. Dear participants, kindly update your display name into your ATAL ID. So keep the microphone on mute. Use chat box responsibly for questions and relevant discussions. Participants are requested to submit daily feedback after submission. Minimum 80% of attendance is mandatory to receive the certificate. Dear participants, kindly complete the feedback form at the end of each session. Dear participant, kindly update your display name into your ATAL ID. Dear participants, kindly update your display name into ATAL ID. Good evening to all the distinguished guests, respected dignitaries, faculty members, and participants. I'm pleased to inform you that our PSV College of Engineering and Technology, one of the most prominent engineering colleges in Tamil Nadu, is renowned for providing quality engineering education, particularly to students from rural background in our own Krishnagiri district, Tamil Nadu. It is a moment of pride for us. Our college has been conferred with autonomous status by UGC and accredited NAC with A grade. We are delighted to host a 6 days ATAL faculty development program online mode on the topic the future of quantum computing and high performance computing. I extend my heartfelt gratitude to AICTE and ATAL Academy for granting us this opportunity to organize this event. I'm thrilled to share that over 750 participants have registered for this FDP, showcasing this growing demand and potential of quantum computing in shaping the future. I encourage all participants to leverage this opportunity to explore and learn about the groundbreaking technology. Now I welcome Dr. M. Srinivasan, Professor and Head of the Department of Information Technology and ATAL Co-Coordinator to invite the dignitaries and the welcome address. We are fortunate to have Dr. M. Srinivasan, one of the key contributors to this program. His expertise and dedication have played a pivotal role shaping this agenda of this faculty development program. Sir, we are eagerly wait forward to hearing your insights. Welcome, sir.
Thank you, Mr. Vinod. Good evening to 100% here. It is my great pleasure to welcome you all to the ATAL online 6 days faculty development program from 23rd December to 28th December 2024. This program is focused on advanced computing with an emphasis on supercomputing and quantum computing. I would like to start by thanking the AICTE Training and Learning ATAL Academy for approving our proposal. We are grateful for the opportunity to host this 1 week online faculty development program. The ATAL Academy vision is to empower the faculties, improve the access, equity, and quality in higher education. We share this vision and promise to support the academy mission through this program. It is an honor to welcome Dr. P. Selvam sir, founder and chairman of PSV Group of Institution. His guidance always inspires us to improve the quality of education. Welcome, sir. Next, I would like to welcome Dr. S. Vivek sir, the secretary of PSV Group of Institution. His support has greatly contributed to the success of this program. Welcome, sir. Next, I would like to welcome Dr. P. Lawrence, sir, principal of PSV College of Engineering and Technology. His dedication to innovation in education motivates us all. Welcome, sir. Next, I would like to welcome all the session resource persons for this 6 days online ATAL FTP. I also welcome all the professors, associate professors, assistant professor, lecturer, and faculty members from AICTE approved institution, along with the PG and PhD research scholars, young teachers, industry professionals, and all the participants to this wonderful 6 days online ATAL FTP. The theme of this faculty development program is the future of quantum computing and high performance computing. These technology are shaping the future of academic, industry, and research collaborations. Over the next 6 days, we will learn from the distinguished expert who will share their knowledge and insights to the audience. This program will provide a very good platform for learning and collaboration. It offers of great opportunity to explore the latest technology that are deriving innovation in various fields. I thank you, our resource person, organizers, and all the my dear participants. This event would not be possible without your support. I encourage each and everyone to engage actively in this session, discussion, and the learning opportunities. Let's begin this exciting journey of discovery and innovation Once again, I welcome to the program. I wish you all productive and insightful week again. Thank you. Thank you, sir. Over to Vinod, sir.
Thank you so much, sir, for valuable and insightful address. It is now time for the lighting of the lamp. Light is a symbol of truth, knowledge, and wisdom. May this lamp illuminate our minds and guide us on the path of learning and growth. As we embark on this enlightening journey into the world of quantum computing and high-performance computing, it is customary to commence our program with the traditional lighting of the lamp.
Vinod, sir, can you increase the volume of your system, Vinod, sir? Once again, play the video and increase the volume of your system, sir. Vinod, sir. Yes. Now little bit audio. Yes, please increase the volume. Yes. Now fine. Vinod, sir.
Yes, sir.
Sir, this, I think system speaker not working. So,
My voice is audible, sir?
yes, voice is audible, but system volume.
Okay, sir. I will proceed for the next session. So now I welcome Dr. P. Lawrence, Principal of PSV College of Engineering and Technology, Autonomous. So it's my pleasure to introduce Dr. P. Lawrence, a visionary leader. He has always been a driving force behind our academic initiatives. Dr. P. Lawrence's passion for integrating emerging technologies into the curriculum ensured that our institution remains at the forefront of education and research. Now I welcome Dr. S. Chandrasekharan, Professor and Head of the Department of CSE and ATAL Co-Coordinator to deliver the speech about the FDP. I am delighted to introduce Dr. S. Chandrasekharan. Dedication to fostering research and innovation has been truly exemplary. His efforts in organizing this program are highly commendable, and we eagerly look forward to hearing insights. Welcome, sir.
Thank you, Vinod. Good evening, everyone. I am Dr. S. Chandrasekharan, Head of the Department of Computer Science and Engineering at PSC College of Engineering and Technology. It's my pleasure to welcome you all to this AICTE-sponsored ATAL Faculty Development Program on the future of quantum computing and high-performance computing. I am thrilled to see around 800 registrations yearly for this program, which is a testament to the growing interest in this cutting-edge technology. So over the next 6 days, from 23rd to 28th December 2024, we will be exploring the latest advancements and applications of quantum computing and high-performance computing. This FDP is carefully designed to provide you with a comprehensive understanding of the principles, technologies, and tools that are shaping the future of computing. Our expert speakers will delve into the recent trends, challenges, and opportunities in quantum computing and HPC, and their applications across various engineering disciplines. Through this program, we aim to equip you with the knowledge, skills, and inspiration to integrate quantum computing and HPC into your teaching, research, and professional pursuits. We believe that this will not only enhance your academic and research capabilities, but also prepare your students for the exciting career opportunities that are emerging in the field. I would like to express my gratitude to AICTE for sponsoring this program and to our team of experts who have worked tirelessly to design and deliver this FDP. Once again, welcome to this exciting journey into the future of quantum computing and high performance computing. Let's work together to explore the vast possibilities that these technologies offers. Thank you. Hand over this session to Vinod.
Thank you so much, sir, for your inspiring, thought-provoking words. Dear participants, keep the microphone on mute. Use the chat box responsibly for questions and relevant discussions. Participants are requested to submit daily feedback after session. Minimum 80% of attendance is compulsory to receive the certificates. Now time to start day 1, session 1. So now I welcome Dr. Nafisha Begum, Professor and Head of the Department of Computer Science and Engineering, Government College of Engineering, Bargur, Tamil Nadu, to deliver the topic, Introduction to Quantum Computing in Computer Science. Dr. Nafisha Begum is a distinguished academician with over 50 publications in national and international journals, a testament to her remarkable contribution to the field. Her expertise and dedication are further reflected in her role as an invited speaker and chairperson at numerous national and international conferences and seminars. Additionally, she received significant external funding for her work from esteemed organizations like Anna University, AICTE, DRDO, UGC, and UPA. Her wealth of knowledge and experience will undoubtedly provide valuable insight throughout this session. On behalf of everyone, I warmly welcome you, ma'am. Dear participant, kindly update your display name into your ATAL ID. So the resource person will join within 2 minutes. Dear participants, use chat box responsibly for questions and relevant discussion. Participants are requested to submit daily feedback for after session. Minimum 80% of attendance is mandatory to receive the certificate. Thank you. Dear participant, resource person will get back in within 2 minutes. Kindly update your display name in your ATAL ID. Dear participant, keep the microphone on mute. Good evening, ma'am. Welcome. Can you please share your screen, ma'am? Nafisha, ma'am, are you there? Ma'am, please share your screen. Nafisha, ma'am, please respond here. Ma'am, please share your screen. Nafisha ma'am. Ma'am, please share your screen. Dear participants, use the chat box responsibly. So participants are requested to submit daily feedback after session. So minimum 80% of attendance is mandatory to receive the certificates.
சார் நான் பேசுறது கேக்குதா சார்?
Yes ma'am, it is audible.
Okay.
Please share your screen ma'am.
Good evening, one and all. Just can you scan one of your message if I am audible?
Ma'am, your voice is clear ma'am. You may proceed.
Okay. Yes, sir. Yes, sir. Just connecting. I don't know why I'm not able to share.
Ma'am, you have a share option. So just click on it and share the screen.
Yeah. Connectivity problem. I'm just doing it. Give me 1 minute.
Okay ma'am.
Sir, can I share the PPT to you? Can you display it otherwise?
Ma'am, you can share the PPT to Srinivasan, sir. We'll share.
Hello. Yes.
Yeah.
Yes, sir. Can I please send me WhatsApp, sir? Just message me, sir. I'll send you the WhatsApp group and link. You take it, sir.
Sir, I have shared to Srinivasan, sir. Can you just check? Connect hotspot. Stop it.
Dear participants, kindly wait for a few minutes. Resource person will share the screen shortly. Dear participants, sorry for the inconvenience. Kindly wait for a few minutes. The resource person will join shortly. Dear participant, kindly wait for a few minutes. Resource person will join shortly. Welcome, ma'am. Kindly share your screen. Dear participants, sorry for the inconvenience. Kindly wait for a few minutes. The resource person will join shortly. Ma'am, once share your PPT, just click on it. So it will share it. Ma'am, are you there? Ma'am, make it in full mode. So now it is okay, ma'am.
23:12 இருக்கும் பாருங்க. Excuse me, are you able to see my PPT?
No, ma'am. So your PPT is not visible. Please click on it and just share it, ma'am.
Entire screen I have clicked. Okay.
Ma'am, again share the screen, ma'am. It is not
shared,
visible.
sir.
Now
I don't know
go to the
what's happening.
PPT, just click on it.
In the PPT, yes, I have clicked.
So just give it share. Ma'am, it is not visible.
Yesterday we tried, no sir, it was coming perfectly.
Yes, ma'am. Yes, ma'am.
Share. Okay. Okay. Now, sir.
Ma'am, please share it. Now it is okay, ma'am. Now it is okay. Just
Can you
press F5.
just
Now it is okay, ma'am.
Now you can start, ma'am. You can start.
I'm very sorry for the delay. Sincerely apologize. There was some power outrage here. So the topic given to me was Introduction to Quantum Computing. I am Dr. J. Nafisa Begum, Professor and Head, CSE Department, Government College of Engineering, Bargur. Can you just tell me if I am audible, one of you?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay. Okay. So we all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that. We are now in the initial stages of the next revolution. We are talking about a new generation of computers, the ultimate computer, a computer that computes on atoms. So, this is the ultimate constitution of matter itself. The question is, who is involved in this race? So, as you all know, all the main industries are fighting for gaining the supremacy in quantum computing. I would like to tell you that this is the ultimate because the main existence of the matter, the atom itself is playing a part here. So the outline of my presentation is quantum technology, quantum computing, what is the advantage, the qubits, operating the quantum computer, quantum computing initiatives by the various people, especially the Indian government, and what to use quantum computing for. Can one of you tell me whether my slides are moving? Yes?
No, ma'am. No.
It's not moving? Outline?
No, ma'am. It is in first slide.
Okay, I'll do it again. So
now it is okay, ma'am. Now it is okay. You can continue.
Okay, I'll show like this then. Okay. So what is quantum computing? Sir, this is visible.
It is visible, ma'am. Make it press it F5 so it is will full mode.
Okay, I'll go by this because if I disturb something, it's going to be an issue. So quantum computing is an emergent field of cutting edge computer science harnessing the unique qualities of quantum mechanics to solve problems beyond the ability or even the most powerful classical computers. So this is the evolution of quantum theory and quantum technology. So the foundations were laid early 90s itself, and then there was some development. There was a Schrodinger equation proposed, which basically told about the superposition of particles, and in 1965 Feynman's theory of quantum electrodynamics was a big breakthrough, and then from 1980 to 2010 we can say it was from theory to practice, and small quantum computers were developed on a experimental basis. One of the major breakthrough was something called Shor's algorithm for finding the prime factors, which made the people think, because it was able to break the number into its prime factors, which was a threat to the cryptographic community. So that made people to get involved more in quantum computing. And then from 2010 to 21 we can say it is commercialization of application. Many companies, many industry, they started developing quantum computers, and commercialization and application of IBM, which provided their quantum computer for use, was also given. And then so this was the development of quantum technology. Similarly, the industry people also, how they kept evolving and how they were involved in the development of quantum computers. This map shows this. You can see that academia and industry were hands to hand, and they tried to develop the quantum computers, starting with 2 qubits computer to a more sophisticated one which we are seeing now. So this is a quantum computing industry which developed, and this is the timeline till 2019. The same thing has been listed here. What are the major milestones in the quantum computing? As you can see, in 1994 the Shor's algorithm, which can break widely used encryption forms, was proposed. This helped the community, or they made this breakthrough made the people to think over to go for a better algorithms which can be quantum resistant, so which could not be broken by the quantum computing also. And then there was this company D-Wave, which also started developing the quantum computers. So this is the roadmap or the milestone of the quantum computers. So here we have the definition once again. Quantum computer, a computer that uses laws of quantum mechanics to perform massively parallel computing through superposition, entanglement and interference. So these three are the main features of a quantum computer, which we will be seeing now: superposition, entanglement and interference. In the case of classical computer, that uses voltages flowing through circuits and gates, which can be controlled and manipulated entirely by the classical mechanics. Now this is a picture of our quantum computer looks like. You can see here it looks like a chandelier. So it's so many circuits, some golden diamond like thing it is seen. So this is the IBM 53 qubit supercomputer based quantum computer. Here we have IonQ, ion trap based 32-bit quantum computer, and we have a Chinese 76 qubit photon based quantum computer. So the idea for this slide is to give us a feel of how the quantum computer will look. It is, of course, it has all the facilities of a modern computer which we use, but due to some reasons, the architecture of the quantum computer will look like this. So as I told you, till now what we are doing is can be called as classical computing, which is the base of modern technology. It works on well-known and proven methods. It consists of binary systems which employs bits that have the value of either 0 or 1. Transistor and logic gates which are the fundamental components that carry out logical operation, and there is a deterministic processing. It follows a predetermined series of instructions to process data, and the most important thing is all our classical computers are based on the stored program concept developed by von Neumann architecture. So von Neumann proposed a stored program concept where he clarified that program and data will be in the memory and instructions will fetch the program and execute on the data and store the result back to the memory. So this is the key characteristic of classical computer. Coming to key characteristics of computer, quantum computing. Quantum computing is truly revolutionary. How it processes information by utilizing the incredible principles of quantum mechanics to offer unparalleled capabilities. So, the main characteristics are, we call the basic thing as qubits. Just like bits, we call here it as qubits, and it can exist in multiple states. It can be a 0, 1 or both simultaneously. This is the major thing which makes quantum computer powerful. So what is superposition? It allows qubit to perform multiple calculations at once because qubit can exist in multiple states at the same time. Entanglement. Qubits can be entangled, meaning that the state of one qubit is dependent on the state of another, no matter the distance. So this is only paving way for nowadays something called teleportation, for which research is still going on. And then quantum interference, utilizing the nature of qubits to enhance the probability of correct solutions. So what are the major differences between classical and quantum computing? First, I told you that the basic unit of information, classical computing uses bits as the basic unit of information represented as zeros and ones, whereas quantum computing uses qubits as the basic unit which can exist in superpositions of 0 and 1 simultaneously. The information processing in classical computing is through deterministic algorithm, whereas in quantum computing it leverages quantum mechanics and uses superposition entanglement to do it in a parallel universe across multiple states. And the nature of computation, it executes based on Boolean logic and electric circuit. Quantum computer utilizes superposition and entanglement to propose and explore multiple solutions concurrently and solve problems probabilistically. And based on the algorithmic approach, we can say that the classical computing has sequential processing and deterministic outcomes, whereas quantum computing employs quantum algorithms that leverage parallelism among the different states, and it is able to solve complex problems like factorization and optimization. Error correction. In classical computing, error correction techniques are well established, whereas in quantum computing, there are challenges with qubit coherence and error rates due to the environmental noise, requiring advanced quantum error correction method to maintain computational accuracy. It is a very big major challenge faced by the scientists across the world for developing a fault-tolerant quantum computer. And hardware implementation, classical computing utilizes silicon-based technologies with transistors and integrated circuits. Quantum computing implements diverse technologies like superconducting qubits, trapped ions, photonic qubits to manipulate and control quantum state of computation. Applications, there are a lot of applications: data processing, software development, internet servers for classical computing. So if we try to use these applications across quantum computing, it is not a justice. it is all very simple applications, and we cannot actually understand the working of quantum computer if you use the same applications. Whereas quantum computing can be used, it holds potential for transformative applications in cryptography, pharmaceutical research, optimization problems, complex simulations that exceed classical computing capabilities. In the development stage, classical computing is well established and continuously evolving, with Moore's law driving enhancement in processing power and efficiency. Quantum computing, ongoing research and development focused on technical challenges and scaling up qubit counts for practical application. So, as per the Moore's law, the size of the chips are getting reduced. So quantum computing is a very big challenge, because now it is going to have a qubits which are nothing but something similar to your atoms. So on December 9th, 2024, some of you would have seen across a video which is being shared, and this is about Willow, which has been a breakthrough by Google. So they have developed a 100 qubit quantum computer. The size of this qubit is the size of this quantum computer, the operating bits qubits is 100 qubits, and they say that we have achieved quantum supremacy. So this Willow, it can reduce errors exponentially as we scale up more qubits. It cracks a key challenge in quantum error correction that the field has pursued for almost 30 years. It performed a standard benchmark computation in under 5 minutes that would take one of today's fastest supercomputer 10 septillion years, one followed by 24 zeros that vastly exceeds the age of the universe. The Willow chip is a major based step on a journey that began in Google 10 years ago in 2011. The vision was to build a useful large-scale quantum computer that could harness quantum mechanics to benefit society by advancing scientific discovery, helpful application. So this Willow was able to achieve it, and here the Google, what they have planned, this is a timeline. So first they were able to be successful with another quantum computing chip called Psycho, and then today, now in December 2024, they have been successful with Willow, and the future research is going to involve using other superconducting devices for the development of the chips and other ions, quantinium. This is the research which is going on in Google. So quantum computers, how do they work? Quantum computers use qubits instead of bits to store exponentially more information. It uses binary code. Qubits processes information differently from the classical computer. So why there is so much of hype? Why there should be a quantum technology? Why people are going to, all industry, academia, and research work is going on in quantum technology? It is mainly because we can expect a quantum economy now. So this is the basic why quantum technology, and the word is heading for a quantum divide. How quantum technology could, these are some examples how quantum technology could revolutionize Africa's health, agriculture, and finance sector towards a Saudi blueprint for a quantum robust quantum economy. So you can see the public sector investments in quantum technologies worldwide. This is the amount they have invested throughout the world, so that they get a breakthrough and they can perform well. Okay. So the quantum revolution, the first quantum revolution resulted in the transistor and the laser. The second quantum revolution was pioneered by people like Karachi and Vineland, establishing full control over individual quantum systems. So in 2012, they were awarded the Nobel Prize for the ability to control quantum systems accurately. So quantum technology aims exploiting the elements of second quantum revolution by superposition, entanglement, and interference. So these are the 4 different sub areas where research work is going on. One is quantum communication, quantum sensor, quantum simulation, quantum computing. So quantum communication is transmitting inherently secure messages. Quantum sensor, improving the measurement technology. Quantum simulation of complicated processes otherwise too hard to simulate, and quantum computing, ultimately solving problems much faster than the ordinary computers. So here, as I told, quantum computer should be used for all the some problems which are currently doing using classical computers, like internet browsing or any other thing which now we have achieved great success through classical computers itself. The main, we go for some better algorithm can be used. So quantum parallelism. So this is again a tribute to Peter Shor of AT&T Laboratories, who gave an idea that we should use quantum computers for task. So as I told you, the 4 key principles of quantum mechanics: superposition, entanglement, coherence, and interference. So now we are going to enter into the basics of quantum computing. So till this, you can see we have seen the introduction, what is quantum computer, what is the evolution of quantum theory and quantum technology with regard to researchers, academia, and industry, how people have played a part, what are the major milestones in the quantum computing, and what are the differences between a quantum computer and a classical computer, and how does a quantum computer look like. Then the basic characteristics of classical computer as well as quantum computer. Then I have listed in some 8 points the core differences between classical and quantum computing. Otherwise, if you see, except for this qubit superposition and interference, both of them have same RAM, they have the circuits, they need power supply for their operations. Those basic things are same for classical as well as quantum computing. And I also said that we are lucky enough to witness the power of Willow, which was revealed on December 9, 2024, up to 100 qubits. And with this, Google were able to say that they have achieved the quantum supremacy, meaning that a problem which would take 10 septillion years to compute has been computed successfully with this Willow within 5 minutes. So what is the future work that Google is going to involve in? I have just listed out. Started with Sycamore, Willow. Now the research is going on for other superconducting materials that can be used for developing the bits, qubits, and other ions. Okay, and then I have just briefly told why there is so much of hype in quantum technology, because it is ultimately working on the atom simultaneously with multiple number of steps, and it is going to revolutionize the world. Different applications can be implemented with better algorithms. People are investing in this computer quantum technology. And the quantum revolution, the main person is Serge Harold and David Heinlein. 4 areas which people are concentrating. All the countries are fighting to achieve supremacy: quantum communication, quantum computing. So the ideology is establishing the power of this rather than going for using the same algorithms which we were using for our entering into our quantum technology or quantum computers. Now, in your classical computer, we have bits, whereas in quantum, we call it as qubits, and each and every qubit can be a 0 or a superposition of both. Okay, so classical bits can be distinct states 0 and 1, whereas here it can be 0 or a linear combination of the two states. It can be measured completely. Classical bits are not changed by measurement, as quantum bits are changed by measurement. They cannot be copied and erased, whereas quantum bits can be copied and erased. So you can see classical computer wants bit at a time. Any number of bits. Suppose you have 4 bits. Bits, know that we can have 16 possible combinations. Even though there are 16 possible combinations, you can have only one bit combination, 0, 0, 1, 1 or 1, 0, 1. Like in the case of quantum computers, we can have one, and it can be a combination of anything, 0 between 0 and 1, which means multiple states. That at the end the output should be only one, whereas with representation it can be in multiple states. Qubits are like arrows. Towards upward, it is a 0. When it is down, it is 1. And if it is in between, whatever value there, that will be coming. Okay. So a qubit can behave like a bit and store either, and be also a weighted combination of 0 and 1 at the same time. When combined, qubits super.
Excuse me, ma'am, your voice is not clear. Ma'am, may I audible? Dear participant, sorry for the inconvenience. So the resource person will connect shortly. Dear participant, sorry for the inconvenience due to the network issue. So the resource person will connect shortly. Dear participant, sorry for the inconvenience. The resource person will connect shortly. Ma'am, are you there?
Am I audible?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Can you please share your screen, ma'am? Dear participants, we apologize for the inconvenience. The resource person will join shortly due to technical difficulties. Thank you for your patience.
Sir, is it same issue?
No, ma'am, it is not
Kindly
shared.
share your screen, ma'am. Your voice is audible, ma'am. Kindly share your
Yeah.
screen.
Was it visible previously? I just wanted to
Yes,
know.
ma'am. Previously it is. It was visible.
Okay, okay.
Ma'am, can you please share your screen? Ma'am,
Ma'am, you can share the screen, ma'am.
so that can
PPT
be
to
visible.
Srinivasan sir. You will take care.
I'm trying, sir. I've shared the PPT. Can you just see, sir?
Oh, ma'am. You can share the PPT to Srinivasan's or WhatsApp.
Shared already, sir. Oh, no, la.
Okay, share your PPT, ma'am. We didn't receive. Otherwise, you can send your PPT to Chandrasekhan sir.
Hmm?
Yeah, now visible, ma'am.
Now it is visible, ma'am. Just go to the PPT, just click on it.
Is it visible?
Yes,
Yes, ma'am.
ma'am. It is visible.
Okay, okay. Sorry for the inconvenience. Okay, so we were discussing about the superposition, and I was okay. So I was telling about superposition. Once again, please confirm, sir, whether the slide is being shown.
Yes, ma'am. Yes, ma'am. Clearly.
Okay, so this is
Yes, ma'am. Visible, ma'am. Visible.
so this is a important theoretical theory which is always given when we are discussing about quantum computing. This is called as the Schrodinger's cat. So there is a poison here, there is a radioactive material available here, and there is a cat which is placed in a box. So to explain the principle of superposition, the cat may be alive inside or it may be dead. We are not knowing it until we open the thing. Okay, until we open the box, the cat is in alive or dead. Okay, so what happens is this radioactive material, if it decays, and which in turn bursts this poison which is inhaled by the cat, and due to this the cat may die or it may be alive. Okay, so this is the theoretical or what is imaginary cat which is given as an example. This illustration is given as an example to help people understand the superposition principle. Okay, so 0 or 1, it is in the same state. Like for example, you can take one more example. We are flipping a coin. So this is also a common example which is given to explain the superposition principle. So when we flip a coin, when it reaches down, we are sure whether it is a heads or a tail. But when it is in the air, in the atmosphere, we are not sure whether it is head or tail. It is a combination of both. Okay, so in fact, the pioneer in quantum computing, Professor Michiko Kaku, he is a very famous physicist working on everything theory. So he says that not only we can say the cat can be dead or alive, it can be sick, it can be dancing, it can be sleeping. So this is what is nature. Okay, so the same thing is followed. Okay, so Schrodinger's cat. So you have a radioactive material, some hanner. This is again one more illustration. Okay, the cat is both alive and dead. It exists in a state of superposition. So you can see here live cat, dead cat. So only when we open the box we can find out. And as Professor Kako has said, only this. It is in so many additional states like dancing. It can be a naughty one. It is wagging its tail like that. So many combinations are possible. Okay. So advantages of qubits and enormous power. Okay. So I think I am repeating this again. Okay. So when you have this many bits in a classical computer, at a time you can have only one Okay, one output, from the input you are deriving the output, you can have only one combination. Whereas in the case of quantum computer, you can have 2 power 10 this number of states simultaneously. Okay, so this is a classical example. So advantage of qubits and enormous quantum power. So adding qubits increases storage exponentially. Quantum power computer doubles the power with every added qubit. For example, we have 32 bits. When you add it, okay, we have to make 64 bits to double the power. Whereas 32 bits have to be added to double the power. Whereas in the case of quantum computer, by just one additional qubit, you will have additional that many number of states. So because of that, you will be able to achieve good things or high parallelism. Can do operations on all superpositions like massively parallel computation. On one math operation on 2 power n numbers encoded in classical computers with n bits requires 2 power n steps or parallel processes, but here with a n qubits we can do it. Okay, so this is the uh, uh, illustration of that. A 64 qubit quantum computer operates in a space of 2 power 64 dimensions, or roughly 16 star 10 power 18 numbers to specify the state of the quantum system. This makes complex problems much easier to solve by quantum computer. I think at least some idea you would have got now. Okay, so parallelly, instead of only 2 bits, okay, so if you have 2 bits, you will have 4 combinations. Okay, but in classical computer only one state, whereas in qubit you will have 4 states. So when the n increases, okay, you have massive parallelism. Okay, so similarly, this is also one more example which is given to give the power of quantum computing. N qubit register can represent 2 power n numbers. Okay, 60 qubits. So some of them what they tell is, why can't we simulate that qubits in our classical computer itself by having so many other concepts like multi-threading, etc., etc. But it is very difficult. Even 60 qubits is hard to simulate on today's supercomputer. So for 300 qubits, which is more than particles in the universe. Okay. So again, I have listed the photograph of Peter Shor, who made people understand that quantum computer is very important by able to define this, finding the factors of a number 32221989. This is the number. So if we given the two numbers, we can easily find the product. But given the number, we have to, it is a very hard problem, but Peter Shor explained that it can be removed or it can be decoded with the help of quantum computer. Okay, so now position, possibility of a qubit to exist in more than one state, that is superposition. Now entanglement is one qubit influence the not only second, whatever qubits are there in the space, it can influence all the qubits. That is called as entanglement. So you can see first qubit, it is more towards the arrow here. So we say it's up to nearing to 0 and it is 60% probability. And second one is lesser. But when two qubits are together, the combination, it is the probability distribution, and accordingly which value should be favored is decided. Okay, this is entanglement. One point another qubit, or it is influencing the other qubit. Okay, so again here number of qubits, number of states, time change. The next important principle is interference. So what happens when you have more qubits? One is that one influences the other. This interference. Actually, visualize this.
Ma'am, please share your screen, ma'am. It's got disconnected. Ma'am, are you there? Participants, we apologize for the inconvenience. Ma'am, are you there? Can you please share the screen? So the resource person will join shortly due to technical difficulties.
Am I on?
Yes, ma'am. Can you please share your screen, ma'am?
The internet slide is shown on the screen.
Ma'am, can you please share your screen, ma'am?
Yes. Sir, please.
Dear participants, we apologize for the inconvenience. Ma'am, are you there? Ma'am, my voice is audible. Ma'am, please share your screen, ma'am. Nafisha, ma'am. Dear participants, the next session will be start by 8.
Yes, repeat the message.
Dear participants, the next session will be start by 8 o'clock. Yes, ma'am. Now it is okay.
Yes, ma'am, your screen is visible. Unmute, ma'am. Your screen is visible.
Ma'am, can you please share your screen? Now it's okay, ma'am. Please continue.
So qubits, is it visible, sir?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay. So the types of qubits, you don't in the case of normal classical computer, we say bits, it is developed from transistors like that. In the case of qubits, we can have different type of qubits: superconducting, trapped ion, quantum dots, photon, neutral atoms. Okay, so this is a picture of superconducting circuits. So you can see copper or aluminium closure is there. There are so many circuits involved. Okay. So an ion trap, it's a combination of electric and magnetic fields used to capture charged particles known as ions. So superconducting circuits are also available. So this is physical implementation, ion traps, superconducting qubits. So you have different types of things, and these are the key terms: superposition, entanglement, decoherence, interference. So we have seen three in this. Decoherence we have to see, in which a system in a quantum state collapses to a non-quantum state. So before going to, so that is the main obstacle. What do you mean by decoherence? Decoherence is the qubits have to communicate with each other. We want them to entangle with each other to have massive parallelism, but they should not entangle with the environment. Okay, so that is the difficulty. Okay, so interaction with the environment can cause coherence. Either it is called relaxation or dephasing. Okay, so like please visualize, there are some waves, magnetic waves, which are in unison in the universe. Okay, so it has to be such that no other external force destroys. Okay, so there should be no noise. Okay, so decoherence is a very general term, loss of purity during the evolution of a system. So there should be no noise coming in, so that you maintain the system. Similarly, dephasing is all the points processed to a same place. Okay, Z noise we call it. That type, the qubits try to move towards the same thing because of some issue in the environment. This should also be prevented. Okay, so this is relaxation and dephasing. Okay, and then noise. The qubits have to be prevented from cosmic rays, radiation, dust particles, heat. That is why all the quantum computers are housed in a very cold temperature, less than 0 degree, so that these qubits perform efficiently. And scalability is also a very important issue. As the number of qubits increases, how do we have massive parallelism among them without having decode. It's a major issue. So superconducting quantum computers, these are different types. One is this, using this method, we call it as a transmon qubit. And then we have silicon spin quantum computers, where these are represented as dots. Everything is quantum mechanics, physics. And we also have linear optical quantum computers, where we try to use photons, okay, for in place of qubits, okay. So that will work for working in unison. Okay, this is trapped ion quantum computers, color center quantum computers, and neural atom in optical lattices, something like an egg box. This is also under development. Other approaches for the development of qubit: electron on helium, magnetic molecule, nuclear magnetic resonance, and cavity quantum electrodynamics. So what are the potential applications? The major thing what it will be very helpful in medical grounds, because people will be able to visualize how the molecules interact, how what makes the DNA problem, what makes the complexity in treatment. So with the help of the parallel computation, people will be able to find out, and the curable will become incurable will become curable. That is the phase which is used for quantum computers. Okay, so this is a map which is based on this quantum computing, and how the so each and every industry, how they will come up, whether what is the criteria they will use. It is not only on the number of qubits. When you go on increasing the number of qubits, the error rates will increase. So we should take care of this also. Crosstalk between qubits has to be done. Connectivity, systematic error, and main thing, the efficiency of a compiler to work on this quantum computer. So all these factors are essential to make that the industry to be top or the forerunner in quantum computing. Okay, so what is quantum supremacy? If any problem which takes a long time to execute is done it in a very fast manner, we say that it is quantum supremacy. And Google claimed 72-bit quantum computer chip Bristol cone to confirm quantum supremacy in the future. But some people, they are not refuting that claim. But now with Willow, okay, actually IBM also has a very good quantum computer, D-Wave Systems,
Ma'am,
Google.
sorry for
Now
the
with,
intro. So the next resource
yes,
person is waiting, ma'am.
okay, just give me 5 minutes.
Okay, ma'am. Okay.
So I just want to cover how, like I showed you, how the countries are playing a part in which we have missed India. So what is the stand of India? The Union Cabinet approved the National Quantum Mission NQM on 19th April 2023. 6,000 crore rupees has been allotted for a period of 8 years for the research activity to be undertaken under National Quantum Mission. So these are some of the things which the National Quantum Mission, already it is 1 year now. So they have achieved some success in this. So as I told, again these also having the four thematic hubs: quantum computing, communication, sensing and metrology, materials and devices, R&D center like IISc and other people are working hard to give quantum computer in India. And the main people involved is the Tata Fundamental Institute of Research in Pune. They have established a lab and they are working on doing this. Okay. So other things I will share the slide, and you can go through. So the major applications, if you see, as I told, medical. And one more thing is, now all these algorithms are no longer secure when you go for a quantum computer. So we need to go for quantum resistant algorithms which cannot be broken by the qubits. Okay, so I stopped this. I think I lost around half an hour without due to technical snack. Anyhow, I thank you for giving me this opportunity and for your patient listening. Thank you.
Thank you very much, ma'am, for your engaging session on Introduction to Quantum Computing in Computer Science. So, dear participant, if you have any doubts or questions, so feel free to ask. So, dear participant, the feedback link is available in the chat box. So, in WhatsApp, YouTube, and WebEx, kindly take a moment to fill out the feedback form. So, dear participant, if you have any doubts, so you can ask. So, dear participant, the feedback link is available in the chat box. So, kindly take a moment to fill out the feedback form. So, it is available in WhatsApp, YouTube, and WebEx. Dear participants, if you have any doubts or questions.
If there are no doubts, can I wind up, sir?
Yes, ma'am. Yes, ma'am. Thank you so much, ma'am, for your
Thank
engaging
the
session.
management. Thank you, sir. Thank you. I thank the
Thank you, ma'am.
management, ATAL, AICTE for giving me this opportunity to explore a new topic. Thank you. Thank you very much.
Thank you, madam. Thank you. Thank you for your wonderful experience.
Dear participant, for the session 1, it's available the link. So just fill it. So the first session 2 have a link. Okay. So you need to fill the feedback link. Dear participant, the feedback link is available in the chat box. So now it's time to start day 1, session 2. So now I welcome Dr. V. Saravanan, Associate Professor at Dolo University, Ethiopia. So deliver the session on the topic quantum gates and circuit design for programmers. So it's my great honor to extend a warm welcome to Dr. V. Saravanan, a distinguished academician with an impressive record of publication in both national and international journals, highlighting his significant contribution to the field. His dedication to research and education has made a lasting impact on the academic community. We are privileged to have him with us today's session, and we are eager to gain valuable insight for his vast knowledge and expertise. On behalf of everyone here, I extend a heartfelt welcome you, sir.
Is it audible?
Yes, sir. You may proceed.
Okay, thank you. Good evening, everybody. I am Dr. V. Saravanan, working as an associate professor in the Department of Computer Science, College of Engineering and Technology, Dambadola University, Ethiopia. Before starting my session, I would like to thank to the PSV College of Engineering, the chairman, principal, and the organizers for giving me such wonderful chance to present here. Now let us go to the PPT.
Your screen is visible, sir.
Okay, thank you, thank you. Okay, let me start. So the session topic is quantum gates and circuit design for programmers. Quantum computing is a groundbreaking field. 1 minute. Quantum computing is a groundbreaking field that merges quantum mechanics with computer science. This section introduces programmers to the fundamental concept of quantum computing, mechanical background, which is required to understand quantum computing, and then qubit and superposition and quantum gates, and followed by circuit design for quantum programming, applications of quantum computing, and finally, we are going to discuss about the challenges in quantum computing. Whether you are a developer or new to programming, understanding quantum computing is crucial for achieving very high-speed computing. So what is quantum computing? We can start with this question. Quantum computing uses the principles of quantum mechanics to process information. Unlike the classical computers that uses bits like zeros and ones, quantum computers use quantum bits or qubits, which can be in a state of 0, 1, or both simultaneously, which we call it as superposition. This property, along with entanglement and quantum interference, enables quantum computers to solve complex problems much faster than their classical counterparts. Is my slide moving? Is my slides moving?
Yes,
Okay.
sir.
Okay, programming for quantum computers presents a set of unique challenges and opportunities compared to classical programming. Here are some key differences with the classical computer and quantum computers. The keyword quantum manipulation is new for us. Unlike classical bits, qubits can exist in a superposition of states. Programming involves manipulating these superpositions and entanglements. The next key difference is quantum gates. Quantum algorithms use quantum gates instead of classical logical gates. These gates operate on qubits and are the building blocks of quantum circuits. Then noisy intermediate scale quantum error. Current quantum computers are prone to errors and have limited qubits. Programming must account for these limitations. But here I like to say one extra point. Recently, the number of qubits are getting added by different companies. And according to the recent news, 504 quantum bits computer are created by IBM company. So the research is going on. Very soon we can expect it as a commercial machine. And another key difference is quantum entanglement. This is totally a new concept. Leveraging entanglement in programming is both a challenge and a source of quantum computers' power. So we can discuss about this quantum entanglement in the upcoming slides later. And hybrid systems. Today, many quantum algorithms involve hybrid systems that use both classical and quantum computers together, which means quantum computers are not functioning alone. It needs some support with other classical computers. So as hybrid system, we are using. This unique environment opens up new possibilities in various fields, such as cryptography, material science, and complex system simulation. Here in this slide, I'm going to discuss what are all the languages we have to work with quantum programming. So we have languages such as Q#, Qiskit, Forest, Circu. These are all the well-known languages. The Q# is developed by Microsoft, and the Qiskit is developed by the IBM company, and the Forest developed by the Rigetti company. Similarly, the Circu, which is very familiar, developed by the Google. Let us discuss all of these one by one. Q#. Q# is a language developed by Microsoft as part of its quantum development kit. It is designed to be used in conjugation with classical programming languages like C# to create hybrid quantum classical applications. Q# emphasizes on seamless integration with existing .NET applications, making it easier for developers with a background in conventional programming to transition into quantum computing. So already many people are familiar with the C#. For them, adapt with Q# is very easy because the syntax and other things are a little bit similar with C#. And the next language we have is Qiskit. IBM's Qiskit is an open source quantum computing software development framework. It allows users to write quantum algorithms in Python, a very popular programming language. So Python is already known for the implementation of machine learning, deep learning, such algorithms, and even it is good in data processing. Now, the same Python is used by this IBM Qiskit. And Qiskit is known for its extensive libraries that covers various aspects of quantum computing, from basic quantum circuit design to complex algorithms and simulations. Forest, developed by Regity Computing, is a quantum programming environment that focuses on quantum classical hybrid computing. It includes Quil, that is quantum instruction language, a language for specifying quantum circuits, and PyQuil, a programming library, a Python library for building and running these circuits on quantum simulators and quantum processors. And the well-known language is Circu. So many people already started learning Circu. Circu is a Python library developed by Google for writing, manipulating, and optimizing quantum circuits. It is specifically designed to target Google's quantum processors. Circu supports the creation of quantum algorithms from the ground up and is particularly adept at handling noise and errors, which is a common issue in current quantum computers. The next thing is we are going to discuss about the mathematical background. To understand the quantum computing in detail, we should be very much strong in the following mathematical concepts. So, for example, addition and subtraction of complex number, that we should know, multiplication of complex numbers, finding complex conjugate, multiplying a complex number with its conjugate, representing complex number on the number plane, magnitude of a complex number, representing complex number in polar form, representing complex number in exponent form, converting the complex number in polar form and exponent form. Starting from this, many topics we should be very strong mathematically to understand the quantum computing in a very strong manner. Till the eigenvectors and eigenvalues. I don't know how much we know already, but by listening this presentation, I hope the listeners, the participants will get some knowledge on all these basic mathematical concept which is required for understanding quantum computing. Let us start the discussion one by one. First, we can start with imaginary and complex numbers. So mathematical teachers or students are very familiar with this, but as a computer science faculties, maybe this is new for us, so I can go slowly. What is an imaginary number? Let us take an equation, x square is equal to 4. Through this equation, if we are asking a question, what is x? So what could be the answer? So we can solve mathematically, x equal to square root of 4, and through that we can solve x equal to 2. So simply we can give the answer, x is 2. So this is a normal calculation. Suppose if there is an equation, x square is equal to minus 4. Suppose in this case, if I'm asking a question, what is x? So definitely we cannot say exactly the answer. The reason is the number is negative, so we can have more than one answer, not exactly one answer. We can have more than one answer. So how we can solve this? We can solve as x equal to plus or minus square root of minus 4. Since it is a negative number, minus 4 is a negative number, answer will come in positive, also in negative. So we can mention plus or minus square root of minus 4. And further, we can simplify this as plus or minus square root of 4, and we can take the square root of minus 1 separately. So in mathematics, the I value, that imaginary value, is square root of minus 1. So square root of minus 1 can be mentioned as I. And by doing that, the final result we can get is x equal to plus or minus 2i. So here comes the imaginary number. So whenever the symbol I is there along with the real number, then we have to understand this is a imaginary number. Imaginary number means that number has more than one possible answers, probably two different answers. So the next one is about complex numbers. So what is a complex number? If a number contains both real number and imaginary number, then it is called as a complex number. The sample complex number will look like this: a plus ib. In general, I'm mentioning a plus ib, where a and b can be a real number, and the I says that b is a imaginary part and a is a real part. So as I said before, real part and imaginary part both is there in a number, then we can call it as a complex number. Let us have some examples. 2 plus 3i is also a complex number because 2 is a real number and 3i is an imaginary number because 3 has i behind it, so we can take it as an imaginary number. So a real number with imaginary number we are having, so that we can say it is an example for complex number. So to understand more, let us have one more example. Square root of 2 plus I square root of 3. This also we can take it as a complex number. The reason is we have a real part and also we have an imaginary part. Similarly, minus 1 minus I can also be a complex number. Here minus 1 will act as a real part and minus 1 will act as an imaginary part. So no need to write minus 1. So directly we have written minus I. I hope you got the idea what is meant by a complex number. Okay, now we should be very clear that how to add a complex number. So everybody knows how to add two real numbers, but there is a small difference in adding two complex numbers. Let us take two different complex numbers. Say for example, 2 plus 3i can be a complex number. It's the first complex number. And we can take another complex number, 4 minus 8i. So now to add these two complex numbers, what we have to do is we have to add real part with real part. I mean first number's real part with second number's real part. And we have to add the imaginary part of the first number with the imaginary part of the second number. So by doing that, we will get 2 plus 4, that is real part plus real part, plus 3 plus minus 8, because in the second number we have minus 8, we are taking minus 8i. So by simplifying this, we will get 6 minus 5i. So by adding two complex numbers, the result will also be a complex number. Let us take one more example. 1 plus 9i can be a first complex number, and minus 3 minus 8 can be a second complex number. We will try to add these two complex numbers. How we can add? We can take 1 and we can add with minus 3. That we done here. And we can take 9 and minus 8. We can subtract either, so we can add both. That is 9 plus 8. So now by simplifying this, we will get minus 2 plus 1i. That is simply I. So this is a complex number again. Subtraction is also very easy. Already we have discussed about addition. I think no need to go much deeper for subtraction. The only difference is we can take real part and we can take another real part, and we should make a subtraction. That is 4 minus 2, and then we have to do 3 minus 7. So the imaginary part must be subtracted with the imaginary part. So in this example, we have 4 and we should subtract with 2. 4 minus 2, it is okay. And we should take 3 from the first complex number, that is 3, and we should subtract with minus 7. Here we have to be very careful. The second number's imaginary part is a negative number, -7. So we have to subtract with -7 and we can add I. So by solving this, 4 minus 2, that is 2, and 3 minus -7, that is 10I. So finally, we got the answer 2 plus 10I. So I think already we have lost some time. We are going beyond the schedule. So one example is enough. I hope you can understand. Now it is very important to understand the multiplication of complex numbers. So addition, subtraction, okay, it is very simple. But in case of multiplication, it is a little bit complex. So we have to listen carefully. So let us take two examples, 2 plus 3i as a first complex number, and we will try to multiply it with another complex number, 4 minus 8i. So what we have to do is, we have to multiply 2 with 4. That is first number real part with second number's real part. That should be done here. And we should take the real part from the first number, and the same should be multiplied with the imaginary part of the second number. That is 2 into minus 8i. That we done here. Similarly, we can do multiplying the imaginary part of the first number with the real part of the second number. That is, we can multiply 3i with 4. So we done here 3i multiplied with 4. And finally, we can multiply both the imaginary part, that is 3i should be multiplied with minus 8i. We done here. All these numbers should be added. So finally, what we will get is 2 into 4, that is 8, and 2 into minus 8, that is 16, and I is there, we can take I, and 3i into 4, that is 3 into 4, 12i, and here we have to multiply 3 with minus 8, that will give minus 24, and here we have I in both the numbers, so I into I square. So by simplifying this, we can do like this. 8 we can take as it is, and here we have minus 16i, and we have another plus 12i. We can join together to get minus 4i, and already we discussed that I is nothing, sorry, I value we have taken as square root of minus 1. The same logic we can apply here. I square can be replaced with minus 1. So finally, the result will be like this: 8 minus 4i plus 24. And by simplifying it further, 32 minus 4i. So by multiplying two complex numbers, the result will also be in the complex number. We cannot get any real number. It can be a complex number. Another example we can take, and we can discuss very shortly. Let us take two complex number, 1 plus 2i, and we can multiply with another complex number, 3 minus 7. So how we can solve this? We can multiply 1 with 3, and then we can multiply 1 with minus 7i, and we can multiply 2i with 3, and then we can multiply 2i with minus 7i. So all this done here, and all the multiplied value should be added together to get the final result. So by simplifying this, we will get 17 minus I. Here you have to note that I square is replaced with minus 1. So already I said I value is taken as square root of minus 1, which means I square is nothing but minus 1. Okay, now the actual topic begins. Complex conjugate. So to understand this only, we have discussed many things. Sorry, my English may be different because I'm working abroad. So according to the local people, my language got changed recently. Okay, so complex conjugate of A plus IB can be written as A plus IB whole power asterisk. So we can specify or represent the complex conjugate by using the asterisk as a power for the complex number. So how we can solve this, or how we can find this complex conjugate? It's very simple. In the imaginary part, simply we have to change the sign. If it is a positive imaginary part, then we can change it as a negative imaginary part. If there is a negative imaginary part, then we should change the imaginary part as positive. So we have to change the sign of imaginary number. So we should not change the sign for both the number. We should change only for the imaginary number. So let us have an example. Here we have a complex number, complex number -2 plus 3i. For that, we should find a conjugate, that is, we are applying the power asterisk. So this can be simplified as -2 minus 3i. -2 we are taking as it is for the real part, but for the imaginary part, I have taken minus in the place of plus. So by changing the sign in the imaginary part, we are getting the complex conjugate. So one more example, if there is a number like 3 minus I as a complex number, so we can find the conjugate by changing it as 3 minus I. So important point, if we multiply any complex number with its conjugate, then the result will be a real number. So previously, in the previous slides, I said that by adding or by subtracting or by multiplying two complex number, result also will come as a complex number. But here, if you multiply a complex number with its conjugate, then it will give a real number. So the complex number won't be the result. The result will be a real number. Let us see how it is. So let us take an arbitrary complex number, that is general complex number without number. Simply, we can specify AB to specify the real part and imaginary part. So let us take A plus IB, the complex number, and the complex conjugate will be A minus IB, that we know. Now, by multiplying, what we should do, A into A, that is A square, we specified here. And we should multiply IB with A. So that also we done here, I, B and A. We can write IAB also, no problem. And sorry, I done a mistake. So A along with A we multiply, that comes A square, and we have to take a multiplication with A and IB, minus IB. So that the result will be minus A, so minus IAB. And then we have to multiply IB with A. So that we have represented here, IAB. And we have to multiply IB with minus IB, that will give minus I square and B square. So by simplifying this, we can take A square as it is, and we can subtract minus IAB, sorry, we can simplify minus IAB and plus IAB, that will become null. So there is a negative value, there is a same positive value. By adding both, it will become null. So we can ignore that, and we can take these minus I square and B square. Further, if you simplify this, we can take A square as it is, and the I square can be replaced with minus 1. As we know, square root of minus 1 is the I value, which means I square is nothing but minus 1. So we replaced I square with minus 1. And we have taken B square as it is. Now by simplifying this, the final result will be A square plus B square. So A is also a real number and B is also a real number. If you know the value of A and B, the final product definitely it will be a real number, not a complex number. So we have a small example understanding this. So here we are going to multiply a complex number with its conjugate. So 2 plus 3i is the complex number I have taken, and we know the complex conjugate is 2 minus 3i. By multiplying both the numbers, we will get 2 into 2, that is 2 square, and we can multiply 2 into minus 3, 2 into minus 3i, that way I mentioned here, and then we have to do multiplying of 3i with 2, 3i with 2, that also I done here, and finally we have to multiply 3i with minus 3i, so that will give I square and 3 square. So now by simplifying this, we will get 2 square minus I6 plus I6 minus 1, 3 square. So now again, here we have to note that I square is replaced as -1. By simplifying this equation, we will get 2 square and 3 square, and remaining all the things will be ignored because we have a negative I6 and a positive I6, we can cancel it. And the final result is 4 plus 9, which can be taken as 13. So we can note that 13 is a real number. It is not a complex number. So this is what I try to insist. We have one more example, but because of time limitation, I think it is better to skip. Now we can discuss about how to represent a complex number on a number plane. So let us take a graph. The graph contains two axes. One is in horizontal line that we can take it as a real axis, and we have a vertical line that we can take it as a imaginary axis. Normally in a complex number, we have two parts, right? Imaginary part and a real part. So for two parts, we have taken two axes, that is real axis and a imaginary axis. Let us discuss about this. We can think a complex number as a vector, and in the 2D graph, we have real axis on the horizontal and imaginary axis on the vertical. This allows us to graph our complex number. The complex number 2 plus 3i can be represented as follows. So let us take an example, -2 plus 3i. This can be a complex number. We are trying to plot a graph, or we try to represent it on a graph. So what we have to do is, in the real axis, we can take the real number, that is -2. So in the graph, we can choose the -2 in the real axis, and we have to take +3 from the imaginary axis. Here it is. So +3 and -2, or -2 and +3 will intersect here in this position. That is specified through the yellow color arrow mark. I hope it is visible for everybody. So this is the point we represented. Complex number. You have to consider the complex number as a vector. What is vector? If we have a single number, that we can call it as a scalar. If we have more than one number, like array, then we can take it as a vector. So we can take -2 and 3 as a single array, or we can say a group of elements, so that we can call it as vector. Now we should understand what is meant by magnitude of a complex number. So in the previous slide, we discussed that how to plot a point in a graph by using a complex number. So now what we are going to understand is, for that particular point, we should calculate the distance from that point to the origin. So the origin is here, the 0, 0 is the origin. From the origin to the point what we specified through complex number, we should draw a line, and we should measure the distance. So that distance is nothing but magnitude. So which can be represented, I mean the magnitude can be represented as -2 plus 3i as a modulus, which can be calculated using Pythagoras theorem as square root of -2 whole square plus 3 whole square. So what it is? The real part whole square plus imaginary part whole square. So this is the equation we got through Pythagoras theorem. So by solving this, we will get square root of -2 whole power 2 plus 3 whole square. That can be simplified as square root of 13. So we can say that the magnitude of this complex number is 13. I hope you understood. So I can repeat since it is very important. Magnitude is nothing but the distance from the center point, that is origin, and up to the point where we specified through complex number. So this distance can be measured. That is nothing but a magnitude. So magnitude can be calculated using Pythagoras theorem, using a formula square root of imaginary numbers square plus complex numbers square. So by applying the Pythagoras theorem, we will get a normal number. So that is the distance, that is the magnitude. Normally in the equations, we will specify the magnitude using a variable r that we can see in the upcoming slide. And in this slide, we are going to discuss about representing complex number in polar form. So up to the previous slide, we know about the complex number, but now in some situation, it is good if you are specifying the complex number in another form called polar form. So how we can write a polar form, that we can discuss here. The complex number a plus ib can be represented using trigonometry as r cos theta plus ri sin theta, which can be simplified as r cos theta plus I sin theta, where r is the magnitude. As I said in the previous slide, r is the magnitude, that is the distance from the origin. And theta is the angle made with the positive x-axis as shown in the below figure. So here we have a figure. The yellow line is the arrow mark, which pointing the exact point we represented through the complex number. So here, for example, we have taken the complex number. Okay, we have taken arbitrary number. Okay, let us discuss generally. So in this graph, let us imagine this is the point specified by the complex number. Now the yellow line says, the amplitude, that is R value. And when you take the angle between this yellow line and the positive x-axis, we can take it as a theta. So now, using the trigonometry theorem or trigonometry concept, we can change this complex number in the form of r cos theta plus I sin theta. So we know the theta because it is an angle we can able to measure, and I will explain how to measure the theta. Here you can see the graph. There is a r cos theta which represents this area, and r sin theta will represent this particular distance. So r cos theta plus I sin theta both taken. This representation is nothing but polar form. This representation is nothing but polar form. A complex number can be represented using a polar form. So we should know how to calculate the theta. In this, we can find the theta using the relation tan theta is equal to P by A. So we have a complex number. From the complex number, we will get P value and A value. So P is the imaginary value and A is the real value. And we can apply the formula tan theta is equal to P by A. And now, through this equation, we can take the theta alone as theta is equal to arc tan P by A. So mathematically, if we find the value for arc tan B by A, we will get the theta value. And by applying the theta value in the equation, we will get the cos theta value and the sin theta value. So easily we can find the complex numbers actual representation value. Okay, now we are going to discuss how we can represent a complex number in another form called exponent form. So in the previous slide, we have discussed how to represent a complex number in polar form, that is using sin theta and cos theta. But in this slide, we are going to understand how it is possible to represent a complex number in exponent form. The reason why we are learning all these things is, in quantum computing, most of the time, we are specifying the quantum positions or the qubit positions using a complex number in exponent form. So it is very important to understand the exponent form. Then we can easily understand the quantum, the qubits. Okay, let us go into the slide. As we discussed in the previous slide, the complex number A plus IB can be represented using polar form as r cos theta plus I sin theta. So this is already known from the previous slide. So this can be represented as r into e power I theta. So we can see it carefully. R, in the equation already we have R, that is magnitude. R is there. The whole equation, that is R cos theta plus I sin theta, the whole thing, we can change it as e power I theta. This is the simplest form for representing cos theta plus I sin theta. So by representing in this way, we can get the exponent form. So here e power I theta. So it is the exponent form. I hope you understood, but we have some example in the next slide. There you can understand more, don't worry. Let's try converting complex number into polar form and exponent form. Let's have an example. Let us take a complex number 1 plus I. So first we can convert this in the polar form. So 1 plus I can be written as square root of 2 into cos pi by 4 plus I sin pi by 4. So how we got this? As we know that from the previous slide, A plus IB can be written as R cos theta plus I sin theta. The same logic we can apply here. R is a magnitude. So by calculating the magnitude using the formula which we discussed before, we will get the result square root of 2, that is R value. R is replaced by square root of 2. And the cos theta, we know how to calculate the theta using the real part and imaginary part. So we have the real value 1 and imaginary value 1. By applying that, we got pi by 4 as a theta value. And now we can apply cos pi by 4 plus I sin pi by 4. Mathematically, what is pi? Pi is nothing but 180 degree. So that we are mentioning as pi by 4. Sorry, pi. So now pi by 4 is very simple. 180 divided by 4, which will give 45 degree. Okay, that also we can discuss in the upcoming slides. So now finally we got the polar form, and now the next work is we have to understand how to represent the same complex number using exponent form. So we already find the polar form, then it is very easy. So we can write the complex number 1 plus I is equal to R. In the previous slide we discussed R into e power I theta. So you can see here the R is already calculated as square root of 2. The theta is already calculated as pi by 4. So we can write simply square root of 2 into e power I pi by 4. So this is the simplest representation of the complex number. So in this exponent form, square root of 2 is the R value and pi by 4 is the theta value. I hope you understood how we can convert a complex number into polar form and in exponent form. Okay, now we can focus on exponent form of a complex number in quantum computing. In quantum computing, we can use the exponent form to represent the complex number because of the property. By changing the theta value, we can rotate around the circle. So this is the important reason why we are learning about the exponent form. See, for example, I have taken a complex number in the exponent form. Suppose if a complex number is 2 into square root of 2 e power I by 4. Simply, for example, we have taken this complex number in the exponent form. So this exponent form represents a specific point that is specified through the yellow arrow mark as usual. And for this yellow line, it is well known that we can measure the angle with the positive x-axis, that is pi by 4. So 90 degree, we know the horizontal line and the vertical line will intersect with 90 degree. Now this yellow line is exactly in center of both the axes. So definitely the angle could be 90 by 2, that is 45 degree. That can be written as pi by 4. So that is not a big issue here. Here the important thing is we should understand in the same complex number in the exponent form, just by changing the pi value, that is pi by 4. By changing this pi value, see how the points will get transformed. So 2 into 2 into square root of 2 e power I pi by 4 will be this point. And if we change the theta value as pi, so minus pi by 2, then the point will come here. And similarly, if I change the theta value as 3 pi by 4, then it will come here. So when we change the theta value, the point will change the position, but all the points will rotate in a circular fashion. Within a circle, all the points will move here and there by changing the theta value. Unless we disturb the real values, just by changing the theta value, different positions we can specify in a circle. So as the first presenter says, the quantum bits always keep on rotating. So to measure the exact position and to specify the exact position, this exponent form is very important. Understanding this exponent form is very important. Okay, and one more magic we can see here in the slide. By multiplying two different complex numbers in the exponent form is very simple, and even the result will fall in the same circle. Let us discuss in detail. Let us multiply two complex numbers, e power I pi by 3. It is a first complex number we have taken for example, and we can take another complex number, e power I pi by 5. So these two complex number in the exponent form, let us assume the magnitude is 1. That's why we didn't mention anything before e. So the magnitude is 1. So this can be multiplied as e power I pi by 3 into e power I pi by 5 is equal to e power I pi by 3 plus pi by 5. So what is the magic here? No need to disturb other values. Simply we can consider the theta value. Here the theta value is pi by 3, and in the second number theta value is pi by 5. Simply by adding these two pi value, we will get the multiplied value. So the multiplied value is e power I 8 pi by 15. So mathematically, by solving these two values, we will get this. So which is perfectly in the circle. So to understand that, I have given two diagrams here. In the first diagram, you can see I have pointed using two yellow color arrow marks. The first yellow color arrow mark points to the location that's specified by the first complex number in the exponent form, that is e power I pi by 3. And second number, e power I pi by 5 is pointed here on the same circle. So after multiplication, the result is e power I 8 pi by 15. So that result also fall in a different place, but on the same circle. So this is a very important property we can use to understand quantum states. So in the upcoming slides, we are going to discuss about the quantum states. There, this will be very much useful. Okay, now we have easy topics. So here I can go a little bit faster. Introduction to matrices. So what is a matrix? So all of us know that the numbers which is arranged in the form of rows and column, the group of values, we can call it as a matrix. So for example, here we have first matrix 1, 0, minus 2, minus 10. So this matrix contains 2 rows and 2 columns. And if you take the second matrix, it has only one column, that is only one column, and we have 4 different rows. 1, 2, minus 3, and 8 are the element values. And even this also a matrix in 2 rows and 3 columns. So 5, 7, minus 2, 2, 3, 1.5, all these things are elements or values inside the matrix. So this is very known, so no need to spend more time here. And most of us know addition of matrices. So how we can do addition of 2 matrices? It is very simple. The first element can be added with the same element in the second matrix. Suppose if you have two matrices like this, as shown in the figure, the first row, first column, we have the value 2. That must be added with the second matrix, first row, first column value, that is 4. 2 plus 4, the result is 6. That can be taken as the resultant matrix row 1 and first row and first column's value. So 2 plus 4, 6. Similarly, we have -3 and +2 in the first row, second column. That can be added to get 9. The same way, we can add all the values in the respective positions, and we can create addition of 2 matrix. It is very simple. Similarly, the subtraction also can be done easily, simply by taking the numbers from same position from both the matrix, that is the matrix A and B, and we can apply subtraction, and result we can take it for the resultant matrix. So for example, in the first matrix, here we have the value 2, and in the second matrix we have the value 3. So we can take 2 minus 3 as a first value, or first value of the result matrix. So 2 minus 3 is nothing but -1. That is the value for the resultant matrix, first row and first column. So finally, we can take one more discussion. Let us take the last value in the first matrix, that is 9. That can be subtracted by the last value, last row and last column value of the second matrix, that is 0. So 9 minus 0, that is 9. So in this way, we can easily perform subtraction of matrices. And the next one is about multiplication of matrices. We know multiplication of matrix, and also we should know how we can multiply a scalar with a matrix. So it is possible to multiply any scalar value. What is scalar? Scalar means a fixed number or a single number. So vector means, as I said before, it contains a sequence of number. So a single number can be multiplied with a matrix. And this is very simple. We can multiply that scalar with all the positional values. So for example, we can multiply k with -4. The same way we can multiply the scalar k with 3, and we can multiply with k with 7. So in that way, we can multiply the scalar value with all individual positions, so that will give the resultant matrix as shown in the figure. Here in this example, we have taken a common value k. Instead of taking 2 or 3 like a normal number, we have taken k, which is a scalar. Okay, and here we have multiplication of matrix. So I like to minimize the time. The first row value from the first matrix can be taken, and the first column from the second matrix can be taken. All the respective positions can be multiplied, and the final results can be added together. Say, for example, 1 can be multiplied with 7, that I have taken here, and 2 can be multiplied with 9. And also, we can multiply 3 with 11. So by doing that, we will get 1 into 7 plus 2 into 9 plus 3 into 11. All multiplication values should be added, so that we will get 58. This 58 we can take as a first value, value for the first row and first column of the resultant matrix. So by repeating this, we can able to fill all the matrix positions. So for example, to find the value, first row, second column value, what we should do is, from the first matrix, we have to take first row and we have to multiply with second column of the second matrix. That will give 64. So by repeating this operation, we can able to fill all the positions. Okay, now we can discuss about column vector. So we know what is matrix and what is column vector. So column vector is nothing but a matrix with only one column, and it can have 2 or more rows. Example I have given here in this slide, 2, 3. It has only one column, but it has 2 rows. So it is a column vector. And in the second example, we have 5, 0, -9 in one column. So we have 3 rows, but only 1 column. So it is also an example for column vector. Similarly, the third one, 6, -3, 1, 1, all these 4 values are in a single column. So this also a column vector. So simply speaking, column vector means we can have more than one value, like an array, but that should be in a single column. That should not be in a matrix, like a normal matrix. It should not be like a normal matrix with multiple columns. Only one column is allowed. Okay, now coming to the important point, we can able to represent a point in a graph using the column vector. Say, for example, let us take a column vector -1 and 2. So this is a column vector. So this column vector can be used to represent a point in a graph. Say, for example, let us assume that the horizontal line is a x-axis and vertical line is a y-axis. So now we can we can take -1 from the x-axis and we can take 2 from the y-axis. The point where -1 and 2 intersects, that is the point. So to represent any specific point in a 2D graph, we can able to use a column vector with 2 rows. So there is a reason why we are discussing this, so that you can come to know in the upcoming slides. So now we can discuss about multiplying a column vector with another matrix. So we know column vector, there is only one column matrix, and it is possible to multiply a matrix with a column vector, and that will give very useful outputs that should be understand to understand the quantum computing principles. Let us take a matrix 1, 2, 2, 1 in this way, and we can try to multiply with a vector 1 and -2. So after performing the multiplication of matrix, we know how to multiply the matrix that we discussed in the previous slide. So by multiplying, we will get the result as -3 and 0. So now let us try to plot a graph for the column vector and also for the column vector what we got after the matrix multiplication. So for the column vector 1 and -2, this is the point. The x-axis, we can take +1, and in the y-axis, we can take -2. So this is the place where both the value will get intersect. And so this is the graph representation for the column vector 1 and -2. After applying the matrix, the result is -3 and 0. For that, again, we will try to plot a graph. We can take -3 in the x-axis and we can take 0 from the y-axis, which means the point will represent here where we have -3 in the x-axis. That is the point, because y is 0. No need to take the arrow mark above. So simply we can keep on the x-axis. So by seeing both the diagram, what we can understand is by applying a matrix or by applying a matrix with a column vector, the graph will get transformed. The point in the graph will get moved from another place. That is called transformation. So we can use matrix to transform a column vector. So that directly we can say matrix is a transformer. Matrix is a transformer for the column vector, or we can say matrix can transform a column vector. Okay, next we can discuss multiplying a column vector with another matrix. So I think time is going. So already we discussed in the previous slide the same thing. Okay, let me skip this example. So now coming to the new topic, the identity matrix. So most of us know about this. Identity matrix is a matrix which contains full of zeros, but only in the diagonal places we have +1. So again, I'm repeating, identity matrix is a matrix with full of zeros, except in the diagonal. In the diagonal, we have only one value, the value 1 in the diagonal. This kind of matrix is called as the identity matrix. So here there is an important property. When we multiply a identity matrix with any column vector, the result will be a same column vector. There will be no change. So previously we said that by multiplying a matrix with any vector will transform the point in the graph. But in case of identity matrix, no transformation can happen. The result will stay in the same point. So that is the important thing. The next thing is we should understand what is meant by inverse matrix. So it will take some time. So shortly I will explain. Suppose if A is a matrix, the inverse matrix can be represented as A power minus 1. So we should be very aware of the property. When we multiply the inverse matrix with the original matrix, we will get the identity matrix. So we know what is identity matrix. Previous slide we have discussed. So when we multiply the inverse matrix with the original matrix, we will get identity matrix. This property is very important in quantum computing. Okay, now a new topic. I think most of you don't know. Most of you may not aware of this. Let me explain slowly. Normally, we can represent the matrix using real numbers like 1, 2, -1, -2 like that. But it is possible we can have a matrix with multiple complex numbers in addition to real numbers. Say, for example, let us take a matrix A that contains value 2 plus 3i, the first row and the first column, and we have 0 in the first row, second column. Similarly, we have 5 in the second row, first column, and we have one more complex number, 3 minus I in the second row, second column. So this is also a way we can able to represent matrix using complex numbers. Okay, the complex conjugate of a matrix A can be represented as A power asterisk. So let us see how we can find the complex conjugate. So we know what's the conjugate. Conjugate means simply we are changing the sign of the imaginary number. So in the matrix A, we can change all the imaginary values, the sign of imaginary values. Here in the matrix A, we have 2 plus 3i as a complex number. Here plus 3 can be changed as -3. That is, we are changing the sign of imaginary number in this complex number. So in the same way, wherever we have a complex number, we have to change the sign of all the imaginary part. So that the resultant matrix will be 2 minus 3i, 0, 5, 3 plus I. So simply I'm speaking, if a matrix contains a complex numbers, complex conjugate can be calculated by changing the sign of all imaginary parts. Another example, here we have a complex number enclosed in a matrix. The complex conjugate, that is whole power star, is calculated by changing the sign of all the imaginary numbers. Okay, the next thing is we should know what is transpose of matrix. So this also I think we are familiar. Most of us are familiar. Let us have a matrix 1, 2, 3, 4, 5, 6. When we try to apply the transpose, we can specify or represented by having power of t. So how we can find the transpose? All the row elements can be changed as a column element. We can say all the row elements can be swapped to column elements. Here we have 2 rows. The first row can be changed as a first column in the resultant matrix, and the second row can be transformed as a second column in the resultant matrix. By changing this, we will get the transpose matrix value. It is pretty easy. So 1, 2, 3, it is in the column here, but in the result 1, 2, 3 in the in the source it is in the row wise, but in the resultant we have 1, 2, 3 in the column wise. So this is the idea how we can transpose a matrix. Okay, there is another important property that is called unitary matrices. So when we combine complex conjugate and transpose of a matrix together as shown below, we will get a new matrix called a dagger, which can be represented using the symbol A plus. This is not exactly like a plus, it is similar to plus. The down part is a little bit lengthier. So we can call this symbol as dagger. So unitary matrix and dagger, we have to understand. Suppose if we apply a transpose operation and one minute. Okay, a single matrix, if we mention both the operations, that is transpose and also complex conjugate, then we will get a resultant matrix that we can call it as A dagger. Again, I'm repeating, if A is a matrix and we know how to find the complex conjugate, that we can represent by a power of asterisk. And for the result, if we apply a transpose effect, then we will get a new matrix that we call it as A dagger. Even A dagger can be calculated as calculated by applying transpose first, and resultant matrix can be applied with complex conjugate. So either first we can apply the complex conjugate operation for the matrix, and then we can apply the transpose operation, or we can apply the transpose first and then we can apply the complex conjugate. So by doing any one of these, we will get the same matrix. That matrix, we call it as A dagger. Okay, and we have another important property. When we take a matrix, let us take a universal matrix or unitary matrix, U, when we multiply A dagger matrix with the original matrix, we will get identity matrix. Or I can say, if we get the identity matrix by multiplying two different matrices, then that matrix can be satisfy the rule. Matrix dagger is multiplied with the original matrix. Or I can say, if a matrix satisfies the condition, matrix dagger is multiplied with the original matrix. If we get identity matrix, then that matrix we can call it as unitary matrix. So I think I confused you. Unitary matrix is a matrix which satisfies the condition. Unitary dagger is when we multiply with the unitary matrix. When the result comes as identity matrix, then we can say it is a unitary matrix. So all the matrices cannot satisfy this condition. Only a few specific matrices will satisfy this condition. The matrix, those who can satisfy this equation, that we can take it as a unitary matrix. I think now you understood it. Okay. When there is a point, when acting on a vector, unitary matrices rotate or flips the vector, keeping the magnitude of the vector the same. This property is useful in quantum computing in handling the probabilities of data. So let us discuss in more detail in the upcoming slides. Okay, we have another matrix called Hermitian matrix. It is the important matrix that we are going to use in the quantum computing. The Hermitian matrix, usually represented by the symbol capital H, is a special matrix which satisfies the following condition. H is equal to H inverse. So when a matrix satisfies that, the matrix which is equal to the inverse of that matrix, then we can say that matrix is a Hermitian matrix. Or we can simply see this equation. If we take two matrices, if inverse matrix and the original matrix both are same, then we can take that matrix as a special matrix called Hermitian matrix. Sometimes when we apply transformation to a vector, the vector may step on the same direction. But if but it may be stretched or compressed. Okay, let me come with an example. So here we have an example in the diagram or figure. We have taken a matrix 2, 1, 2, 3. So this is a matrix. So this first matrix is going to multiply with a column vector. The column vector contains the value 0.5 and 0.5. So when you try to plot a point in a graph for this vector 0.5 and 0.5, so this is the point. The point is represented by orange line. And after multiplying this matrix on this column vector, we will get a result 2, 2. So we know that the matrix can be taken as a transformation of a vector. So that is already, again, it is going to be proved here. So this vector 0.5 and 0.5 is multiplied with this transformation matrix that got transformed to a new point 2, 2. When you plot the new point 2, 2 on the graph, we can take 2 from the x-axis and 2 from y-axis, and this is the point. Now, when you see the graph carefully, the orange line and the new yellow line, both are in the same, both fall on the same line. Only the distance changed. So this, we can say that the vector 0.5 and 0.5 got stretched. Sometimes by applying this kind of operation, the vector will get compressed. So compressed or stretched, both the things can happen during the calculation. In our example, the vector got extended, I mean, it got stretched. So when we have such kind of vector and such kind of matrix, then we can say that that vector is called eigenvector. And from this result of the eigenvector, we can take a, we can take a scalar out. So for example, from the vector 2, 2, we can take the value 4 out from this vector, so that we can get the original matrix back. We can get the original vector back. So 0.5, 0.5 is the original vector. After a transformation, we got 2, 2. Again, by taking a scalar value or a fixed value out from the vector, we can get the original vector. So if a vector and a matrix satisfies this condition, then there comes a new concept, eigenvectors and eigenvalues. So here in this example, this vector is a eigenvector, this matrix is a matrix, and the 4 is a eigenvalue. So that is very important, eigenvalue. So to understand that eigenvalue, we discussed these many. So in one line, I can finish this. When we apply a transformation matrix on a vector, then if a vector got stretched or compressed through the new result, then we can call it as the original vector is a eigenvector. And if we take a scalar, if it is possible to take a scalar out from this vector, then that scalar is a eigenvalue. I think it is good if we discuss with one more example. This is a matrix 2, 0, 1, 2. If this matrix is going to be applied on a vector 0, 3, then we will get the same 0, 3 with a eigen value 2, which means by multiplying these two, actual output is 0 and 6. 0 and 6. Commonly, it is possible to take 2 out from this vector. So now these 2 will act as a eigenvalue, and this vector 0, 3 will act as a eigenvector, and this matrix is a transpose matrix. So why we are taking this as example for eigenvector and eigenvalues? See the graph. Before applying the transformation, the point lies on the y-axis, that is represented by the orange color, and after transformation, the value goes up to 6, that is represented by yellow color. So when the graph, in the graph, if the R value get increased in the same direction, that is magnitude get increased in the same direction or compressed in the same direction, then there we can have eigenvalue and eigenvector. So eigenvalue and eigenvector cannot be taken for all the matrix, and we cannot take for all the vectors. Only for few we can take it. Okay, now I think you are very much interested to learn what is a qubit and a superposition. So as of now, we have completed the all fundamental knowledge required to handle the qubits and the superposition. So now it is easy for us to understand what is a qubit and what is a superposition, how we can manipulate the qubit. Everything is easy. Let us go through the slide. So classical computers use zeros and ones for storing and processing data. But the quantum computer uses qubits that we can call it as quantum bit for processing the data. A quantum bit can be a 0, sometimes it can be a 1, most of the time it can be both, which means we cannot say exactly it is a 0 or 1. It can exist in both the position. That we can call it as superposition. So this is the major difference between normal computer and the quantum computer. Physically, a qubit can be made from any quantum particle that has two distinct states. Say, for example, if you take a photon of a light being polarized either horizontally or vertical, sometimes the photon will rotate horizontal wise and vertical wise at the same time. So this is the best example to understand a qubit. So another example already given by the first presenter, when we toss a coin on the air, when we catch the coin, then we can say whether it is in the head position or it is in the tail position. But when it is rotating on the air, it is impossible to say whether it is in a tail state or it is in a head state. It is unknown. The coin stays in both the state at the same time. So this is the best example to understand what is a qubit. So in quantum computing, we can represent the states using column vector. So this is the reason why we discussed many mathematical background. So now in the classical computers, we can specify the state as 0, right? By writing simple 0. But in quantum computing, we can represent the state or position 0 as cat 0. So the symbol, there is a vertical line, then we have a 0 and there is a greater than symbol. All these things together, we can call it as cat 0. We can spell like that. The 0 state of a quantum bit, we can represent using a column vector 1 and 0. Similarly, in quantum computing, the state 1 can be represented as cat 1. That can be represented using the column vector as 0, 1. So you may confuse why 1, 0, 0, 1, why 2 value. So it is very usual, but when we are passing next slides, you will get what it is. Mathematically, we can represent a qubit as a column vector with 2 elements as follows. So we can represent the state of the quantum qubit state using this symbol called psi. We can call the whole state as cat psi. So cat psi means indirectly it is a state of a quantum or a quantum bit or qubit. So the qubit state is unknown. Continuously it will change, right? So that we are using this notation for understanding it is a qubit state. So the qubit state we can representing using a column vector with alpha and beta values. The top element alpha indicates how much the qubit is in cat 0 state, and how much the bottom element indicates how much the qubit is in one state. So the qubit will persist in both 0 and 1 state. So the alpha value specifies how much it stays on the 0 state and how much it stays on the 1 state. The state cat 0 can be represented using 1, 0 using a column vector. So what is the meaning? The 1, 0, the column vector 1, 0 represents that the qubit is fully in 0 state and none in the 1 state. So the top position always says how much probability the qubit stays in a 0 state. So here we have 1, which means the qubit stays fully in the 0 state, and in the bottom we have 0, which means it specifies the qubit is not there in the 1 state. So totally the qubit is in the 0 state. To represent that, we are using the column vector 1 0. Similarly, the position 1 can be specified by the column vector as 0 1. The same meaning here. The top we have 0, which means 0 position is 0, but the 1 position is 1. In mathematics, actually the probability value will fall between 0 and 1. The maximum probability is 0 in mathematics, and the minimum probability is 0. So in the first case, in case of state 0, the full probability we have given in the 0th position, and the minimum probability we specified in the bottom position, so that we can say it is in the position 0. Similarly, here the 0th position is totally null, that is 0. But the probability of being in position 1 is full, that is 1. 1 is the maximum probability, so that it is representing the state cat 1. Okay, now we can have a discussion on measuring a qubit. When we measure a qubit, we only measure a 0 or 1. If we were to measure a qubit represented by cat psi and represented by a column vector alpha beta, we would not measure the alpha value or beta value. We will still measure only the 0 or 1. So already I said that the top value says the 0 probability and bottom value specifies the 1 probability. So the alpha always specifies the probability of 0 and beta value always specifies the probability of 1. We are not measuring the alpha beta value. By taking the alpha beta value, we can able to measure the probability of the qubit value. Okay, and here important point is here. After measuring the qubit, the position changes to either 0 or 1 depending on the measurement. If we measure the qubit as 0, then the state will collapse. How we can understand this is, when we toss a coin, the coin is keep on rotating in the air. We don't know what is the exact position. If you measure the coin for head state, means you are catching the coin with head state. So after catching the coin state will collapse, which means the rotating state will be collapsed and the state will stay constantly on a head state. So this is an example for how we can measure the qubits. So whenever we are measuring the qubit keep on rotating. So when we are measuring it for 0 value, it will stop in the position 0. And after that, it will not spin again. It will stop permanently in that position. And if you measure the qubit position as 1, then qubit will collapse into the 1 state. So we will have only the state cat 1. So this is very important property we have to understand. So in a qubit, the probability of measuring 0 is the magnitude of alpha value. So mathematically, when you apply the magnitude for the alpha value, and then when you apply the square, the whatever the value we are getting, that is the probability of getting the 0 state. And the probability of measuring the qubit as or qubit state as 1 is magnitude of beta square. So we know the beta value from the column vector. If you put the beta value and if you find the magnitude and the square, the resultant will tell you how much probability the qubit is on the state 1. So here one more thing. After finding this magnitude and the square of alpha and the magnitude and the square of beta, we will get different probabilities. Sometimes we will get 0 here, 1 here. Sometimes we will get 0.5 here and 0.5 here, or even 0.3 here, 0.7 here. But there is a relationship. When you add both the probabilities, the result probability should be 1. As I said before, in mathematics, the maximum limit for the probability is 1. So that condition should be satisfied. So it is quite hard to understand. Better we have an example, and we can find these qubit state, and also we can cross verify whether the qubit state is valid or invalid. So the example, let us take a sample qubit specified by the symbol cat psi1. Why we specified cat psi1? Cat psi1 says at some point 1 the circuit or in the quantum computation, we have a state alpha value square root of 3 by 2 and beta value 1 by 2. And for this qubit, if we want to measure the probability of being 0 and probability of being 1, then we can apply the formula what we discussed before. The probability of measuring the qubit as 1 is the magnitude of alpha value, that is square root of 3 by 2 whole power 2, that is square, will give the result 3 by 4, which is 75%. And the probability of measuring the qubit as 1 is we are taking the magnitude of the beta value and we are squaring it. Mathematically, when we solve this, we will get the answer 1 by 4, which is 25%. So from these 2%, we can understand the qubit maximum it will be in the 0 state and minimally it will be in the 1 state. And also it is interesting if you see that when you take the probability of being 0 and the probability of being 1, if you add both the probabilities, we will get the answer 1. How? By adding 3 by 4 plus 1 by 4, the result will be 1. So the qubit state also valid and our calculation also valid. If by adding both the probability, if you are not getting 1 exactly, then we should understand there is an error in the system or error in our calculation or error in our measurement. Okay, the next thing is we should know how to validate a qubit states. I think we discussed just before in the previous slide. It is good if you take example, no problem. If a qubit state is square root of 3 by 2 and 1 by 2, here square root of 3 by 2 is the alpha value and 1 by 2 is the beta value. When you find the square of both alpha value and beta value, we are getting 3 by 4 plus 1 by 4, which gives the result 1. So that we can say that the qubit state is valid. We can consider that for further calculation. But as the first presenter said, that qubits or quantum computing already have high chances of error because of.
Sorry for the interrupt, sir. So
okay.
Time is out, sir.
Oh, sorry. I can go faster, no worry. How much time I can take from now? Okay.
2 to 5 minutes, sir.
Okay. So we should understand the Dirac notation. So there is a special notation called Dirac notation to specify the quantum bit or to specify a qubit. So normally we can specify the qubit using a column vector with alpha beta value. When we change it as it in another form, like the qubit state is equal to alpha cat 0 state plus beta cat 1 state. It is a transformation, right? If you are changing in this way, this is called a Dirac notation. So Dirac notation can be cross-verified as like this mathematically. When we take alpha beta as 2 vector like this, alpha 0 plus 0 beta, then we can take the alpha out from the first vector and beta out from the second vector. Then we can change it as alpha 10 plus beta 10. So already we know 10 is the state of cat 0 state, right? 10 is the vector value for cat 0 state, and 01 is the vector value for cat 1 state. So now we can simplify that as alpha cat 0 state plus beta cat 1 state. So this way of representing is called Dirac notation. And we have an example. So later we can share this PPT to all the participants so they can go through this example for better understanding. Okay, now we should understand how we can able to represent the qubit using a block cipher, a block sphere. Let us take a spherical shape. It is a 3D diagram. We have three different axes: x-axis, y-axis, and the z-axis. So the z-axis is vertical. When the yellow color arrow mark, or we can take it as a stick or a cut. So when this cut falls vertically, then we can say the qubit is in 0 state. If this cut is lying in a vertical state but in an opposite direction, then we can take the qubit is in 1 state. If the qubit is not in vertical position, and if it is not in the negative vertical position, it is somewhere in between these two, then we can take it as a intermediate position. And also, if the yellow color arrow mark, that is cut, falls on the x-axis, then we can say it has a positive imaginary part, or it has a negative imaginary part if it is falling on the negative side. And in the y-axis, if it is falling, and if it is on the negative I side, then we can take the magnitude is in that position. So it will take some time. But anyhow, simply I can summarize here. We can point the quantum state anywhere in the circle based on the value of alpha, beta. So the point may be in the top or bottom or somewhere. So this point says the actual probability of being 0 or being 1, being negative or being positive, or being with different magnitudes and phases. Only one example. Let us take a qubit with state 1 by square root of 2 as an alpha value and 1 by square root of 2 as a beta value. Then we can represent the same using the Dirac notation. How we can represent in a Dirac notation the alpha value into the cat 0 value plus beta value into cat 1 state. So this is a Dirac notation. The same thing we can represent on the graph. When you represent it on the graph, it will stay here. It is not going towards 0. It is not going towards 1. It is exactly in the equator. So that this qubit, the state will be have 50-50 chance. 50% chance it will be in a 0 state, and 50% chance it will be in a 1 state. So we have many examples. I hope this slide will help you to learn further. Because of time limitation, I'm moving. Okay. In quantum computing, we have quantum circuit building blocks called gates. So in the classical computer, we have many gates like AND gate, OR gate, NOT gate, XOR gate, etc. to manipulate the binary values. Similarly, to manipulate the quantum bits, that is qubits, we have many gates that we are going to discuss shortly. But we can group these gates into two types: single qubit gates and multi-qubit gates. Okay, let us discuss about the single qubit gates. There is a gate called Pauli transformation gates, and there is another gate called Hadamard gate. So Pauli transformation gate have three types: X gate, Y gate, and Z gate. So X gate is nothing but it is similar to NOT gate in the classical computer. Whenever a quantum qubit is coming as an input to the X gate, the X gate will give the output as by changing the qubit, or it will shift the qubit exactly 180 degree in the x-axis, and then it will return. So let us have a diagram here. In this first diagram, you can see that qubit is in the 0 state, which means the yellow line is a very vertical, and the arrow mark is towards z-axis, so it is a 0th state. If this state is given as input to the X gate, then the output from the X gate will be like this. The position will get swapped or we can say flipped 180 degree in the x-axis so that it will turn towards the value 1. So see the second diagram, the yellow color arrow mark points the point which is very near to the cat1 state. So whenever we are passing a 0 state, x gate will do the reverse and it will give a positive value or state 1 value. So or simply we can say x gate will rotate the x-axis 180 degree. Similarly, when you take y gate, when you give a input, a qubit as an input, the y gate will flip or change, or it will rotate 180 degree in the y-axis. That's why the gate name is y gate. And we have another gate called Z gate. So this Z gate, what it will do is, it will take a qubit as an input, and it will flip, it will change the z-axis exactly 180 degree, so that the output will be like this. So the y gate and z gate are not written for changing the value. Simply it is created to change the position. I mean, simply it is used to flip the position in a different axis. So x gate will shift the position 180 degree in x-axis. Y gate will shift the position 180 degree in the y-axis, and the Z gate will shift the qubit position in the z-axis exactly in 180 degree. So we have many interesting things. We have discussed all the mathematical background to understand these things, but because of shortage of time, just we are running. But no worry, I will share the entire PPT to the organizers, and they will forward it to you. So by going through this slide, definitely you can understand. And if I get one more chance to meet you all again in future, I can explain in very detail on these things. So the second gate is Hadamard gate. So Hadamard gate is a different gate. Previously, X gate, Y gate, and Z gate simply twisted or flipped the point towards some axis. But the Hadamard gate is somewhat different. It will twist or flip the qubit in y-axis, not in 180 degree. Instead of twisting in 180 degree, it will twist in 90 degree, that is pi by 2. So other gates will flip the position 180 degree in different axes. But Hadamard gate is a gate which twisted the qubit in y-axis, but only in 90 degree. So this is the major difference. So mathematically, we can perform Hadamard gate by applying the transpose matrix. So in the previous slide, I said that a matrix will act as a transformation for a vector, right? Qubit can be represented by a vector. Matrix can act as a transformation. So now if you take all the gates, X gate, Y gate, or Z gate, whatever, every gate have a transformation matrix. So for example, Y is having a transformation matrix 0, I, 0. Similarly, if you take X gate, transformation matrix is 0, 1, 1, 0. And Z gate, if you take transpose matrix is 1, 0, and 0, 1. So all these gates will act as a transformation matrix, and all the qubits we are representing using a column vector. When we apply this gate matrix, this gate transformation matrix and a qubit vector value, then definitely it will give a different point on a graph, right? So that is the work done by all the gates mathematically. But when you take graphically, it is very easy to understand. It fits in a specific degree, in a specific axis. And we have another two important gates, C0 gate and the controlled X gate. C0 gate is a gate which takes two qubits. So one qubit will act as a target qubit, and another one will act as a control qubit. If we are passing two qubits in different states, say for example, if you pass 0 state in the first suppose if the first qubit is in the 0 state and we are giving another qubit as a 0 state, then this C0 gate, how it will work is, whenever the control qubit is 1, then the X gate will work here. Otherwise, no gate will be worked. So if you pass 1, the 1 will travel to that end if the control bit is 0. If you pass 1 in the target, if the control qubit is 1, then here X gate principle will be applied so that the output will be different. So if you pass 1 as an input, then the output will be 0 if the control qubit is 1. If the control qubit is 0, then no action will be performed on the first qubit, that is target qubit. The same thing we can done through mathematically. Here I given two different colors, 0 and red color. So the 0 will act as a first qubit and 1 will act as a second qubit. When we apply C0 gate, whenever the first qubit is 1, the second qubit will get changed. Same way here in this example, the last question you can see, we have two qubits, 1 and 0. First qubit, that is control qubit, it is 1, so that the second qubit got changed. And we have a last gate, Foley gate. Foley gate is it is almost like a X gate, but double the time we have a control bit. So when we are giving a qubit as an input in 0 state, the output will be 0 state if any one of the control qubit is 0. When both the control qubits are 1, then the X gate operation will be performed on the target bit. So for example, if you give state 1 as an input, and you can give 1 in the second qubit and 1 in the third qubit, then the target qubit will perform X operation, X gate operation. So the 1 will be transformed as 0. It is like a NOT gate in the classical computer. If any one of the control gate is not 1, then that action cannot be performed. Whatever we are giving as input, the same thing will go as output in the target bit. The last topic is about the quantum circuit. So far we discussed some gate like X gate, Hadamard gate can be represented by H. So many gates we can connect in series and in parallel to form a quantum circuit. To perform different algorithms, different operations, we have to arrange these quantum gates in any one of the form, like serial form or a parallel form, or maybe combination of both. So now let me give a short explanation, exactly 1 minute. Let us take 3 qubits. So we are giving input 0 and 0 state as a second input, and a third quantum bit is specified as state 1. When we are giving these 3 qubits in these 3 states, how the circuit will perform? The first qubit will travel from left side and it will start moving towards the right side. While moving, in between we kept a X gate, so that 0 state will be transformed as state 1 in this point. And if we are measuring in that point, the maximum probability is we can measure it as a 0. And when you see in the second line of the circuit, when we are passing a quantum bit in 0 state, while passing through X gate, it will be changed as state 1. And when it passes through the Hadamard gate, the Hadamard transformation will be applied, so that 50-50 chance of 1 and 50-50 chance of, 50% chance of being 0 and 50% chance of being 1 will happen at this point. If we measure for 0 and 1, we will get 0.5 probability for both. And if you take the third one, when we pass a quantum bit 1 from left side, it travels in the right side, towards the right side. That time it will cross again X gate. So definitely when we measure, the maximum probability is 1 will get converted to 0 state, and the maximum probability we will measure it as 0. So this is a small example how the quantum circuits are working. The same thing we can understand mathematically. And a very, very important topic in quantum computing is quantum entanglement. So I think it is good if I spend 1 more minute. Look this circuit. We have only 2 circuit lines. The first is in the first circuit line, we are passing a quantum bit with 0 state, and it is crossing a Hadamard transformation. So Hadamard transformation, it is a matrix mathematically. It is a transformation in a specific angle in y-axis in 90 degree. If you are discussing in physically, I mean using physics, if we discuss, it is changing the angle in y-axis with 90 degree. When we discuss mathematically, Hadamard is a matrix. It is a transformation matrix that can be applied on the qubit 0. So now, after crossing the Hadamard gate, the possibility of getting 0 and or 1 is 50-50. And this output is again given as a control bit or control qubit for the second bit. So we discussed before, based on the control bit, the target bit will work. So now Hadamard gate will give 50-50 chances of being 1 or 0 state. This gate will work 50% of the time it will work, and 50% of the time it won't work. So when we represent the same mathematically, the output will be like this. 2 qubits, the output will be like this, 0, 0 or 1, 1 state. We have 2 qubits in the output. So we are specifying mathematically as cat 0, 0 state and cat plus cat 1, 1 state. So this is the output of this circuit. So now if you see, when first qubit is 0, definitely the second qubit also 0. When you check or measure the second qubit, if you measure the first qubit as 1, the second qubit also 1. From this, what we can understand is, from this circuit, it is sufficient to measure any 1 qubit, so that we can understand the output of other qubit also. So if the first qubit is measured as 0, then definitely the second qubit output also it will be 0. No need to measure. If the first qubit is measured as 1, then definitely the second qubit output also 1. So without measuring both, by measuring any one, we can easily find the state of other qubit. So what I'm trying to say is, if we have a 2 qubit, by measuring 1 qubit, we can easily know the state of another qubit. This state, we call it as quantum entanglement. So first qubit is linked or connected to the second qubit. So by finding the first qubit value, first qubit state, we can able to find the state of another qubit without measuring, even if it is away from here. Even if we are keeping this in a different universe or different Earth, it is possible we can find the state of the next qubit. So this way of representing 2 qubit by connecting is called as quantum entanglement. It is a power of quantum computing. So last 10 seconds, IBM provides an online interface to make a quantum circuits. They provide an interface. Through the interface, we can drag and we can drop all the gates, and we can create multiple circuits. We can connect each other, and we can perform operations as we need. And results also we can see instantly. Since we are here and we don't have a real quantum computer for working on it, so we can go for these kind of online simulators. So the simulators will help us in working with quantum circuits. The circuits uses quantum gates. So as a beginner, it is best if you visit a website, algassert.com. That is shortly algorithm asset. The website shortly mentioned as algassert.com. If you visit this website, you can see a wonderful interface, very, very simple. There you can drag the gates, X gate or Y gate or Z gate, and you can keep on a specific circuit line, and you can add any number of circuit lines. You can connect each other, and you can see the output, how it is working. So by doing that, whatever we discussed before in the previous slides, everything you can see practically. So I had a plan to show you the demo, but unfortunately, because of time limitation, I'm just skipping that. And applications, already the first presenter said about that, no need to explain. And challenges also, the first presenter completed. One point I like to say, quantum computers are very much sensitive for the external disturbance. So we should take additional care while writing algorithm for quantum computers. And I want to show the interface of the website, what I said before. So this is the interface. So we can drag the X gate, we can put it on a specific circuit. We can even create many, we can create many qubits. So see here, I have given state 0 as input for the X gate. So 0 means it should be off, right? But the output is on. Here, see another X gate. If I give the state 1 as an input, the output is off, which means it is 0. So the X gate simply changes the state from 0 to 1 and 1 to 0. And same way, you can drag the Y gate, you can drag the Z gate, even you can have a CC NOT gate by having the connectors, or a CC NOT gate like the gate which we discussed, Toffoli gate. So that also it is possible to create the circuit, and we can give different inputs in this simulator, and you can examine the possible outputs. So this way you can understand each gate practically. So thanks for listening my presentation. Really very big thanks for your patience. Uh, uh, I know that I skipped many slides and I went very fast in the last moment, but I am very satisfied that I have given you a very strong mathematical background for you. This will help you to understand the quantum computing. If you verify any online sources, previously you might have feel difficult to understand what it is. But now after this section, if you take any other reading material from anywhere, definitely it will make you feel easy. So that the satisfaction I have, and now I'm going to complete this session. Thank you really.
Thank you very much, sir, for delivering such an insightful and engaging session.
And I like to say one thing, if participants have any queries, even they can send the queries to my email ID, and I have a WhatsApp number, plus 251 is the country code, 94626 5942. So this is my WhatsApp number. They can communicate with me through this WhatsApp number also, since we have less time. I think that is a good way we can clarify our doubts. Okay, sir, thank you.
Thank you, sir. Thank you so much. So dear participant, the session 2, the feedback is link is available in the chat box. So it is available in WhatsApp, YouTube and WebEx. So kindly take a moment to fill out the feedback form for the session. So it is mandatory. So the link is valid up to 10 p.m. today. So dear participant, the feedback link is available in the chat box. So kindly fill it. So thank you very much, sir.
Thank you, sir.
Thank you, sir. Participants are requested to submit daily feedback after session. So day 2, session 3. So tomorrow at 6 to 7:30 p.m. So resource person Dr. G. Fatima, professor and head of the department, Computer Science and Engineering, Adiman College of Engineering, Hosur, Tamil Nadu. So day 2, session 4. So we'll start by 7:30 to 9 p.m. So resource person Dr. P. Sobana, software developer, BrainSwing Educate Private Limited, Chennai. Dear participants, the feedback link is available in the chat box. Dear participant, those who have completed with the feedback, so you may leave the WebEx. So day 2, session 3 will start by tomorrow 6 to 7:30 p.m. So the resource person, Dr. G. Fatima, Professor and Data of the Department, Computer Science Engineering, Adiyaman College of Engineering, Hosur, Tamil Nadu. So day 2, session 4, so starts by 7:30 to 9:30 p.m. So resource person, Dr. Shobana, Software Developer, Brainswing Educate Private Limited, Chennai.